So welcome to this first colloquium of 2018. Today's event is devoted to chemistry, and I will be very briefly anticipating the next ones. The next one will be held on February the 14th and will be devoted to the history of science, which is a novelty for this series of seminars. The following one will be held on March the 7th, and it will be devoted to gravitational waves and the new discoveries. And the next one will be held on April the 18th, and it will be devoted to biology. As usual, at the end of this colloquium, there will be some simple refreshment on the other side of this floor, so you're all welcome to participate. So let Chiara.
So welcome again, and I'm particularly glad to introduce our guest today, Professor Pat Vaccaro from the Yale University in the US. Professor Vaccaro got his PhD in 1986 at MIT under the supervision of Professors Robert Field and James Kinsey, working on the development of novel laser techniques for state-selective preparation and state-specific detection of molecules in regimes of extreme low vibrational excitations. After 4 years as a postdoc at Stanford University, in the group of Professor Richard Zare, he moved to Yale, first as assistant, then associate and full professor since 1998. Professor Vaccaro has got many awards, acts as a reviewer for many diverse scientific journals and international funding agencies, and is also a member of the editorial board of the journal Chirality. His research activity strives to elucidate the origins of molecular behavior by probing fundamental physical properties and chemical propensities. Ongoing experiments exploit diverse forms of linear and nonlinear laser spectroscopy, many of which were pioneered in his lab, such as polarization-resolved resonant four-wave mixing and cavity ring-down polarimetry. The main aim of the studies is to unravel the intimate coupling among electronic, nuclear, isotopic, and environmental degrees of freedom that govern molecular structure and dynamics. And when combined with synergistic computational analysis, such information permits to get a deep understanding of many chemical phenomena, including proton transfer, non-covalent interactions, solvation, and chirality. And this last, chirality, is the topic of today's colloquium. So, please.
Okay. Now I just need my talk. Oh, okay. Thank you very much. And I want to give special thanks to Chiara Capelli for arranging for this visit and for making it a very wonderful experience. This is my first time to Pisa, and I'm really in love with the city. So I've been asked to make this a relatively general talk, and I will try to give some general introduction. But the work that I'm going to talk about today, that's me, is going to be a collaborative effort between my group, and I'm a physical chemist. And it was really started in collaboration with a group of Ken Weiberg, who he's retired now, but it was a physical organic chemist at Yale. So it's a very collaborative endeavor. Looking at phenomena that we call optical activity. So let me give you a little bit of background here. I hope this works. But this is going to be a talk involving the subject of chirality, or intrinsic handedness. Now, chirality is an everyday occurrence, but our many daily encounters with chirality essentially go unnoticed. Mundane events, such as the putting on of one's shoes, the greeting of an acquaintance with a handshake, the admiration of the beautiful spiral patterns that you might find on common seashells or garden snails, or even the appreciation of architectural wonders such as a spiral staircase. All of these are everyday manifestations of chirality that or intrinsic handedness, but we really don't pay much attention to them. Likewise, the concepts of chirality permeate nearly all aspects of modern science, ranging from the physics of fundamental particles, through the stereochemistry of organic molecules, onto the structure and function of macromolecular complexes that govern the fundamental processes of life. And chirality even has implications of cosmological importance, having to do with the formation of galaxies and the generation and other celestial bodies. We're not going to be able to cover all aspects of chirality in science in this talk, clearly. We're going to focus on a particular aspect. In particular, we're going to focus on the effects of chirality in molecular science, in particular the stereochemistry or three-dimensional arrangement of atoms in complicated molecules. This drawing over here is from a Swiss artist, Hans Ihre. And it first was shown during the 1975 Nobel Prize lecture in chemistry of Vladimir Prelog. The title of his talk was Chirality in Chemistry. And it demonstrates the essential ingredients we need for dealing with chirality. We have to have human intellect, we have to have a right and a left hand, and we have to have two enantiomorphous tetrahedra. And you'll see where that comes into play. The particular aspect of chirality that I'd like to talk about today are the processes where we take chiral molecules, molecules that have intrinsic handedness, and interact them with chiral light, light that has intrinsic handedness. And this gives rise to a set of phenomena that are collectively known as optical activity. So the processes we're going to talk about are trying to understand the unique signatures one finds when one interacts chiral molecules with chiral light. So if we get started, so molecules can come in what are called enantiomeric pairs. They can come in a right-handed form and a left-handed form, which are mirror images of each other. So they're non-superimposable mirror images. If we look at the name of this particular molecule, so limonene tells us something about the arrangement of carbons and hydrogens in this molecule. And so it gives us a general idea of what the structure of this molecule might be. The other objects that appear in this name, the R and the S, for example, tell us something about the absolute stereochemistry or the absolute arrangement of atoms in space in these two non-superimposable mirror images. And let's understand, these non-superimposable mirror images, they will have identical chemical and physical properties as long as they are in an environment that does not distinguish chirality. So in theory, both of these molecules will have the same boiling point, they'll have the same melting point. If one uses conventional spectroscopy like infrared spectroscopy or nuclear magnetic resonance, you will get the same spectra. As long as you're using something that doesn't distinguish handedness, you're going to have identical properties. But of course, if you have something that distinguishes handedness, and you don't have to look much further than your right and left hand to realize biology is very handed, then these molecules can do different things. And that's why knowing which molecule you have can be very important, especially in the pharmaceutical world, because one-handedness of a molecule could be therapeutic, the other could be carcinogenic or worse. Okay. So the R and the S tells us something about the absolute configuration, the absolute arrangement of atoms in space. Older designation is this plus and this minus. This plus and the minus is telling us actually what happens when we interact a chiral molecule with chiral light. So plus, for example, would mean that at a specific wavelength of light, and that D there indicates sodium D-line light for historical reasons, 589.3, this molecule has what is called a rotation, or it rotates the plane of polarization of light by plus 123 degrees or so. This minus tells us that at that same wavelength, this particular molecule rotates the plane of polarization in equal magnitude but opposite direction. So if one could do a measurement of this polarization rotation, one can obviously then distinguish between these two molecules. But the distinguishing that you can do right now, if you just did the measurement alone, is a relative measure, is a relative distinguishing. Because you can really say, okay, whatever the sample is, it has a positive rotation. I can't assign that positive sign to a structure from first principles. Here, okay, this one has a negative rotation. I really can't assign that sign of rotation from first principles until recently. Recently meaning it is now possible to do quantum chemical calculations that can predict the sign of this rotation and therefore turn a relative measurement such as this polarization rotation into an absolute determination of configuration. Okay. And this has really it initiated a renaissance in the field of chiroptical spectroscopy, that is the use of spectroscopy to try to distinguish the two mirror images of given molecules. Please.
How are we going to do about separating these distinguished objects?
So there are many ways, but they have to be based on chiral interactions. So, for example, one thing that can be used is chromatography. So you have a substance which is coated with another chiral object. You pass these through, and you get differential retention on the column. And so they actually separate if you go through a long enough distance. So you can definitely separate them using, again, chiral means. So as I said, it is now possible to predict the sign of this rotation and therefore turn a relative measurement into an absolute measurement. And so part of the reason we started to do the experiments I'll discuss today is to analyze how good are these computations at the present stage. I might also tell you that, without having any sort of sophisticated optical techniques, you could actually tell these two apart relatively by yourself by using chiral receptors in your nose. Because one of these will smell very much like an orange. The other one, well, some people say it smells like a lemon. To me, it smells like refined turpentine or something like that. It really doesn't smell like a lemon to me. But you can certainly tell them apart just by using chiral receptors in your nose. We cannot compute which of these molecules yet, maybe we will soon, smells like an orange and which smells like a lemon. But if we could compute those properties, that would also provide a way of converting a relative measurement of structure into an absolute measure of structure. Now, when I talk about chirality, especially when I talk to colleagues in chemistry or to chemistry departments, and I talk about optical activity, they're usually thinking about an environment like this. And this looks like a sea of molecules, in particular a sea of benzene molecules, but it actually represents a very dilute solution. If we swing around in this dilute solution and zoom in, we'll see that in the middle of the sea of benzene sits a lone chiral molecule. And from a physical chemist point of view, this is a very complicated system. We have a chiral molecule that's going to interact with chiral light, and although we understand the basic mechanism that causes this interaction, and we'll talk about that momentarily, implementing it in molecules is still not trivial. But you can clearly see that this molecule can interact with its environment, right? It can interact with the sea of benzene that surrounds it. And I'll show you that those interactions can have profound consequences, can truly change what we measure. So our experiments have been designed and are really the first quantitative efforts to remove this complication, to remove the perturbations from the environment and look at what I call intrinsic optical activity, the optical activity of a molecule that has been isolated from any perturbing influence with its surroundings. And hopefully, if we can understand the optical activity of an isolated molecule, we can then go back and understand what solvents or what solvation might be doing. But I think you'll see that we really have a long road to solvation here. We're not really there. We don't understand. So let's talk about these optical activity signatures that I keep mentioning. So they can be broken into two parts. There's circular dichroism. Circular dichroism is a resonant effect. It has to do with the differential absorption of left circular and right circular light. So the idea is if we take a linearly polarized beam of light, it can be decomposed into coherent superposition of right and left circular polarizations. Pass this linearly polarized light through a material that is circular dichroic. One of the components is going to get absorbed more than the other. The light, after it leaves the sample, is going to be elliptically polarized. You measure that ellipticity, you can learn something about the chirality. If you don't specifically care about the chirality, you can use this as an analytical tool. And circular dichroism is often used in biophysics and biochemistry. If you have a macromolecular sample and you want to know how much of it is helical and how much is in sheet form, you can do a circular dichroism experiment, use empirical rules to interpret the chiroptical signatures that you get out, and therefore determine the composition of your macromolecular sample. So this is a resonant effect. You take the light and you tune it to the place where the molecule absorbs. Really pioneered at the turn of in the 1900s, early 1900s, by Aimé Coutan. An older technique by 80 years or so is the technique of circular birefringence. This is a non-resonant effect. You typically monitor it in places where light is not getting absorbed. And this comes from differential retardation, a difference in the index of refraction for left and right circularly polarized light. And the index of refraction is what determines how fast light travels through a substance. So again, you take a linearly polarized beam of light, pass it through a material that is circular birefringent. One of the components is going to pass through faster than the other. The light, after it leaves the sample, is going to be linearly polarized but rotated. One enantiomer is going to rotate the polarization clockwise. The opposite enantiomer is going to rotate the polarization equal amount but counterclockwise. And so that's what provides a mechanism for determining the relative discrimination of two chiral molecules. So we're going to be focusing on this phenomenon of circular birefringence. Now, circular birefringence, as you can see from the dates down here, has been known for over 200 years. And for 200 years, it has been studied with great profit in the condensed phase. Liquids, solutions, powders, crystals. We've learned a lot about chiral molecules and their interactions from those experiments. The experiments I'm talking about today are taking molecules out of the condensed phase where they like to be and putting them in a rarefied vapor phase. Most chemists, when I tell them I'm going to do that, look at me strangely and say, well, why would you ever want to do that? Why you want to do that is shown graphically here. This is what is known as an optical rotatory dispersion plot. It shows as a function of the wavelength that we're applying, and these are wavelengths that span the near ultraviolet to the invisible. As a function of wavelength that we apply to a sample, the measured polarization rotation. So the polarization rotation can be clockwise, positive, or counterclockwise, negative. And this particular polarization rotation is normalized, so we have degrees normalized by the length of the path length in decimeters, and normalized by the concentration of chiral molecules in grams per milliliter. And this is what chemists typically call specific optical rotation. All these curves are for this very small and simple chiral molecule, which we'll talk about initially, dissolved in high dilution in all of these common solvents in chemistry. So high dilution means we don't have a solute interacting with another solute. It means we have a solute surrounded by a homogeneous shell of solvent, nominally. And you can see, depending on what solvent I pick, I get a completely different curve. We teach in second-year organic chemistry that if you make a solution of an organic molecule, pick whatever solvent you want, and you do a measurement of this property, typically at a wavelength of 589.3 nanometers, sodium D line, you get a characteristic property, or you measure a characteristic property of the chiral solute. Clearly, that is not true. You're measuring a property that is being highly perturbed by the surroundings, right? And you can imagine if you're developing a quantum chemical way of predicting these curves. The predictions on isolated molecules are very difficult. Solvation models are coming along and are getting better and better. But if you do a calculation on an isolated molecule, and this is the only data you have to compare against, what curve do you pick? Well, a wise theoretician would pick whatever curve agrees best, obviously. But clearly, I can do a mixed solvent system and give you any answer you want in this system. Okay. So what can solvents do to change optical activity? So we have to understand a little bit about optical activity to understand what a solvent might do. And so what we're trying to do is measure a polarization rotation. It's related to this difference of index of refraction for left and right circularly polarized light. The theory behind this was developed classically at the beginning of the 1900s, and then was developed quantum mechanically 1 year after Erwin Schrödinger postulated his famous equation. And so this is the historical definition of the index of refraction difference as formulated first by Leon Rosenfeld, a protege of Max Born. And it's an interesting expression that I just want to take you through a few aspects of it. It's proportional to the number density of the chiral molecules that you're interacting with, so it's a linear concentration dependence. And then it involves a sum over all the excited states of the molecule. So sum over all the excited states of the molecule is the signature that this is a composite property. It's a property that depends on the entire electronic distribution of the molecule. It doesn't depend on a localized distribution, it depends on the entire electronic wave function. What are we summing over? Well, we're summing, if we look in the denominator here, we have a difference between the excitation frequency of each excited electronic state in the molecule and the frequency of the incident light that we apply. So you can see that if we go into resonance here, something bad might happen, and we'll talk about that in a second. But what we have appearing in the numerator is what is known as a rotatory strength. It is a product of electric dipole moment and magnetic dipole moment transitions connecting a ground electronic state to an excited state. So that means to have this quantity be non-zero, you simultaneously have to have magnetic and electric dipole transitions from a ground state to an excited state. This will not occur simultaneously if the system has any symmetry. Chiral molecules, by definition, do not have high symmetry, and therefore these simultaneous transitions can exist. So this rotatory strength is an interesting quantity. Why that particular form? I like to try to justify that a little bit. So it's a product of an electric and a magnetic dipole moment. So an electric dipole operator is proportional to the linear momentum operator, and linear momentum is what generates what we call a translation. So if you want to think about a transition that involves an electric dipole moment operator, and a good example of that is in a carbonyl compound. If you're going from a pi bonding molecular orbital to a pi star anti-bonding molecular orbital, you're going to want to calculate an integral that is non-zero and has net overlap. Because this wave function is orthogonal to that, if you just take a product of them and integrate, you would get 0. But if you put a dipole moment operator in between, it's a translation operator. So if you take, let's say, this molecular orbital and translate it along the CO bond and then calculate the overlap, you get a non-zero quantity. So the electric dipole moment operator part acts like a translation, is what I wanted to say. The magnetic dipole part, on the other hand, is proportional to an orbital angular momentum operator, which is a generation of rotation. So the kind of transition you would have here is epitomized by a non-bonding molecular orbital going to a pi anti-bonding molecular orbital. If you were to just take this function times this function and integrate over all space, you would get 0. You put a magnetic dipole operator in between, it's going to take this function and rotate it. And then you take an overlap with this and integrate over all space, and you get a non-zero value. So this acts like a translation, this acts like a rotation. You put them into optical activity, you have a translation times a rotation, which means the effective transition moment is helical. So you have an effective transition moment that is helical, which is going to interact with light that is either right circular, right helical, or left circular, left helical. They're going to interact in different ways. One enantiomer of a chiral molecule will have a right-handed helical form for the transition moment. The other enantiomer of a chiral molecule will have a left-handed helical form for the transition moment. So they will act completely oppositely and completely differently. It has to do with a subtle interference effect between the electric and the magnetic dipole moments, which give you either a right helical or a left helical transition moment. Okay, so this is the historical expression, but clearly something bad happens with the historical expression. If we happen to take our color of incident light and tune it into resonance, we get a pole in the denominator, which certainly isn't good. So if you do this with more modern perturbation theory, you get a electric dipole, magnetic dipole polarizability tensor that has built into it the fact that excited states don't live forever, ever. They have dephasing or damping processes. In this case, the pole is removed. So if we can look down here, the real part of this, which gives us circular, the imaginary part, which gives us circular dichroism, is in green. This would be an absorption-like line shape. The imaginary part, which gives us circular birefringence, is in red. This gives us a dispersive profile. If we take this expression and take the limiting case where the damping or dephasing rate goes to 0, which means the excited state lives forever, we get back to the historical expression. The historical expression says that we have basically an infinitely sharp absorption and we have a pole in the dispersion profile. Okay. Now, the way it's written here is a sum over all the excited states of the molecule. And clearly, if we're thinking about this form and thinking about a quantum mechanical calculation, the reliability of a quantum mechanical calculation is really going to depend on how well that calculation can reproduce the excitation energies and the transition moments of the chiral species. But this summation converges very, very slowly. So it's not typically what is used in quantum chemical calculations. Instead, what is used is linear response theory, basically exposing the wave function to electric and magnetic fields and see how it responds. And that gives us something that is able to calculate this difference of index of refraction. So what does a solvent do? A solvent can change everything on this slide. A solvent can certainly change transition moments. A solvent can certainly change where the excited states are located. And solvents can certainly change these damping or dephasing rates. So everything can be changed by a solvent. The obvious way to remove the complication of solvation is to take the molecule out of a solvent into the vapor phase. Why, if this has been studied for 200 years, are we the first to do this? We're not the first to do it. There were 4 historical attempts prior to us. 1815 is the first. Jean-Baptiste Biot, who is really one of the pioneers in studying optical activity. He's also got a famous name in terms of magnetic phenomena. But he was studying at that time optical activity in quartz crystals, discovered the 2 right and left-handed forms of quartz crystals. He then started to study quartz crystals dipped in liquids to see what the effect of the surrounding liquid would be. So what liquids do you have in 1815? Well, you have water, very important liquid, not chiral. But you also have chiral liquids like lemon juice, orange juice, and what I call tree juice, or distilled sap from a tree, which gives you turpentine. So one day he's looking at a quartz crystal dipped in a beaker of turpentine. He pulled out the quartz crystal and he saw, my word, the turpentine itself is still rotating the plane of polarization. Now this is an important discovery because they didn't know about atoms or molecules, but they knew this piece of quartz was a solid, it was rigid. The liquid, as far as they knew, didn't have any periodic structure. But he did see that the quartz crystal, which is dense, has a big rotation of optical wavelengths. The liquid, less dense, has a smaller rotation, but definitely there. He wanted to confirm that maybe, the liquid had little clusters in it in some way. So he decided to go to a rarefied environment. He decided to go to a vapor. And he saw, okay, Quartz crystal, big signal. Liquid, less dense, less signal. Gas, probably even less signal. So he would have to compensate with path length. So he rented the largest building in town, which was the church, and he put in it this apparatus shown in the background, which consists of a 50-meter long tube. And he knew he would have to put in the highest pressure possible, which means he would have to boil the liquid to basically get an atmosphere worth of pressure. So what we have is this apparatus. We are polarizing light by reflection. Professor B.O. is over here looking through the analyzer. His assistants, I guess we would call them graduate students now, are over here getting the sample ready on an open flame. And the sample they chose to study first was turpentine, distilled extract from a tree, and turpentine and open flames don't go well together. So here he is, his assistants are boiling the open vat of turpentine. Professor B.O. is over here and he's seeing the polarization signal appear. He's very excited. He calls his assistants over to confirm. Just then, the entire apparatus burst into flames. Everyone escapes, the church burns down. But in his memoirs, he states, or he encourages others to repeat this experiment, but and this is a quote, "Be careful or you'll die a most miserable and painful death." So this is the first experiment, 1815, repeated in 1864 by Guernes, who's a protege of Louis Pasteur, again in Paris, this time outdoors, looking at, again, 50-meter long tubes filled with the vapors of active liquids, lemon juice, orange juice, tree juice, turpentine. Repeated again in 1895 in Paris, this time looking at the vapors coming off of fermentation products. The only modern attempt, Lowry and Gore at Cambridge in 1931, looking at camphor and camphorquinone, multiple meter long glass tube filled with these compounds heated to a high enough temperature to give enough vapor pressure. They saw there was an effect when they were close to the absorption, and don't forget when you get close to the absorption, you get that pole, you get a big increase. But as they moved away from the absorption, the signal died rapidly. So to my surprise, prior to our experiments, no quantitative measurement of this. Why? I mean, this is what we're trying to do. We're trying to measure a polarization rotation. It's proportional to concentration, proportional to path length, and this proportionality constant is actually what we want because it tells us the rotation per path length per concentration. Now, one can buy a commercial instrument to do this measurement in the solution phase. In the solution phase, the commercial instrument is typically based on a 1 decimeter or 10 centimeter path length, and you typically need a good fraction of 1 mole concentration for a typical organic molecule to get enough of a rotation to measure. You take those numbers and convert to the vapor phase. In the vapor phase, even for a very volatile organic molecule, the concentration has gone down 4 orders of magnitude. To compensate, you'd have to increase path length 4 orders of magnitude. Now at Yale, we have a very nice big campus, okay? So this is, shows one of our colleges, undergraduate living buildings at Yale. And I can certainly then, stretch an apparatus throughout the college and try to do this experiment. But I would first of all go broke trying to fill it with chiral molecules. Plus, I'd have to ensure that the density is the same everywhere, the temperature is the same everywhere, the pressure is the same everywhere. And I haven't drawn all the curious undergraduates that would be constantly touching the apparatus. Not to mention the fact that it could blow up, right? So we don't do the experiment that way at all. Instead, we do it on a tabletop. So how do we do this? Now, a very common technique now in molecular spectroscopy is this idea of cavity ring-down spectroscopy. The basic idea is you have 2 very high reflective mirrors, 99.99+% reflectivity. You inject a pulse of light inside these mirrors. The light bounces back and forth thousands of times, and you look at the little bit of light that leaks out the other end. This provides a way to do, for example, absorption over effective kilometers worth of path length. Can you use this technique to do measurements of optical activity? Not directly. If you've ever, stepped in front of your bathroom mirror, you hold up your left hand, the reflection is your right hand, right? That's because when light retroreflects from a mirror, it actually inverts its helicity. Right circularly polarized light coming into a mirror comes off effectively left circularly polarized light. So if you just had a cavity like this, and you inject a pulse of linearly polarized light, and you have chiral molecules inside, you would accrue optical rotation as you pass through, hit the mirror, invert helicity, cancel optical activity as you pass back, hit the mirror, invert helicity, accrue, cancel, accrue, cancel. That would be great, but you'd only have, 1/2 of a round trip path length, not the kilometers of path length you need to do these measurements. So this is where we came up with a new technique. The technique is called cavity ring down polarimetry. It's based on using tunable light sources, tunable laser sources, very modest conventional laser sources having a nanosecond duration pulses coming out. Again, we have a high reflectivity cavity formed by two mirrors. And we put, the key to making this all work are the optics that we put into the cavity. Those optics correct for the handedness change that light experiences upon retroreflection. So the basic idea of how this would work is with these optics out here and this optic here, we're able to inject a linearly polarized field in the middle. And this central region is the region that is sensitive to natural optical activity. With this optic here and these optics out here, we take this linear polarization and project it onto two orthogonal channels of linear polarization detection. And this way, when we put in a chiral vapor, we can monitor the change in polarization of the light as it goes back and forth thousands of times in the cavity. So this is the world's most sensitive polarimeter by many, many orders, maybe 4 to 6 orders of magnitude. It is the only instrument in the world that can do these measurements, that has the exquisite sensitivity to do these vapor phase measurements. I like to say those lofty statements so then you won't laugh at me when I say this is also the world's least versatile polarimeter. Let's realize that to make this work, we have to have the best reflective coatings we can on those mirrors. We have to have also the best anti-reflection coatings we can on those intracavity optics. That can only be done over a narrow range of wavelengths. So every time we want to change the wavelength substantially, we have to completely replace all the optics in this apparatus. So we have exquisite sensitivity, but very limited wavelength or frequency agility. But let me just prove to you that it works the way a polarimeter should. So these are measurements done at a wavelength of 355 nanometers on good turpentine, alpha pinene, okay? And what I'm going to show you is the measured polarization rotation in angle, which is in millidegrees per effective decimeter of path length, but we're literally going through 1 to 3 kilometers worth of the gas. So measured polarization rotation as a function of the pressure of the sample that we put in. So if we take 1 enantiomer of this chiral alpha pinene and put it in, we get a nice straight line because we should have a linear dependence on concentration. We get a 0 intercept, no chiral molecules, no rotation. That's the way it should work. And the slope here is telling us the rotation per path length per pressure, convert pressure to concentration, and we get specific rotation in the units chemists are familiar with. We take the opposite enantiomer of this molecule, and we have, again, a linear dependence, 0 intercept, that's good. Now the slope has the same magnitude within experimental accuracy, but the opposite sign, the way it should for the 2 enantiomers of a given chiral molecule. Now what if I take these 2 chiral molecules and mix them equally together? This is what we would call in chemistry a racemic mixture of the 2. A racemic mixture of the 2, no response at all in this experiment as it should, because they cancel each other, right? So clearly it's working the way a polarimeter should. What does it tell us? So this is that molecule I showed you in that movie earlier, methyloxyrane or propylene oxide. I've shown here a subset of the lines that we obtain in very dilute solutions for different solvents. And then you see two black dots. Those black dots are vapor phase measurements. Again, exquisitive sensitivity to make these measurements possible, but very limited wavelength agility. We have good optics at 355 nanometers and at 633 nanometers. And these optics are good because those two wavelengths represent fixed commercial laser wavelengths, where you can acquire the optics readily. But even from these simple measurements, we can see a couple of things. So the first thing we can see here at 355, in all these common solvents, the molecule acts optically like it's left-handed. You take it into the vapor phase, the sign is changed. It's acting optically like it's right-handed. That's a big difference. Second thing we learn is, okay, if you ask most chemists, what solvent should I pick to mimic isolated molecule behavior? Now, most chemists will obviously tell you to pick a solvent that doesn't interact strongly. And solvents that don't interact strongly are not very polar. They have sort of a uniform charge distribution. They don't have a lot of functional groups. So most chemists might tell you to use something like this deep blue curve here. That deep blue curve is cyclohexane, an alkane. And it's got the right shape, but you can see a better mimic here is the green curve. Green curve is acetonitrile. Acetonitrile is a molecule that is extremely polar. No chemist in their right mind, using their intuition, would say that is a good mimic for isolated molecule behavior. But we routinely find for rigid chiral molecules, the solvents that best mimic what we see in the vapor phase are non-intuitive solvents. Non-intuitive solvents can include acetonitrile, and in some circumstances can include water, where no chemist would tell you those are the right solvents. And there's a good reason for this that I hope I have time to get to. Okay. Third thing, we got into this to thinking about calculations. So if we do everyone's favorite level of calculation, a density functional theory, which is very efficient, you can see if we do a density functional theory calculation with a typical augmented double zeta basis, the shape looks right. It's in good agreement over here, maybe not so good agreement over here. Improve the basis set quality. And okay, it's gotten better over here, but it's gotten substantially worse over here. And in fact, I'll show you in a minute, if you keep improving this calculation, it moves it right off of our experimental data. On the other hand, now what if we do the gold standard calculation? Whereas a couple cluster calculation nowadays for this size molecule can be done in a fraction of a day. What if instead we do the gold standard, which is a couple cluster calculation, which is still a very difficult calculation to do, but everyone will agree is the saturated limit of electronic response. And now this isn't our work, but you get a curve that looks like that, and that's very bad, obviously. And in fact, it's so bad that people at first thought that our experiments were wrong. Okay. There are actually error bars on those points. Deep inside, this experiment has been repeated on 3 generations of the apparatus. Right? There's no doubt our experimental points are right. Also, there's no doubt that this is the saturated limit of electronic response. So what's wrong here? We're dealing with, however, with an actual molecule that has electrons, but it also has nuclei. And those nuclei are not just sitting there doing nothing. This shows, for example, what is known as a torsional potential. It shows the potential energy as you take this methyl group and let it rotate on the oxirane ring. And you can see that there are 3 equivalent minima because you have threefold symmetry here of this methyl group. So there's nothing special here, and one can go ahead and quantize the levels in this potential. And I'm showing you here the vibrational probability distributions. Nothing special here at all, until you also do a prediction of the optical rotation as a function of rotation of this methyl group. And you can see the optical rotation swings from wildly positive through 0 negative, wildly positive through 0 negative. The electronic structure calculations I showed you on the previous slide were done at the single equilibrium point structures. All 3 are equivalent. They were done at those single points. The real molecule doesn't live at the bottom of the potential, right? It lives in the 0 point energy level, And so the appropriate thing to do is to do a vibrational average, at least to average over the 0-point energy of the molecule. And if you go ahead and apply that vibrational average to this electronic calculation, it puts it right on to our experimental data points. So from this simple experiment, we've learned 3 important things. Am I running out of time? No, okay. We've learned 3 important things. Solvation can alter dispersive optical activity so much it could change the sign. The best mimics for isolated molecule behavior are provided by counterintuitive solvents of high polarity. And what has hitherto really been believed to be a purely electronic response, at least in situations where the electronic response is relatively small, can be overwhelmed by vibrational contributions. So let's talk a little about solvation now and models of solvation. And I feel, bad showing a slide like this here because PISA is really the center of solvation. The models I'm talking about were certainly pioneered here in Pisa by Professor Tomasi, among others, right? So this is really the center of solvation. But 2 generic models of solvation. One, an explicit model where you treat the solute and the solvent as a supramolecular complex. This allows you to treat accurately the first solvation shell, which is a critical region for discussing interactions between molecules and their surroundings. But it typically provides a poor description of the long-range effects associated with solvation, and obviously becomes very computationally expensive as the size of the system grows. On the other hand, the implicit models, where you treat the solvation as a continuum dielectric, obviously you're neglecting the important first solvation shell effects. You do get an accurate description of long-range solvent-solvent interactions, and this is computationally expedient. The best of both worlds is to combine the 2 together. And combining the 2 together, being done in several places, but notably here by Professor Capovelli. So the idea here is we're going to talk not so much about explicit models, I'm going to talk about implicit models. And the polarizable continuum model is really the progenitor of this. It probably should be called the PISA continuum model, okay? But we're going to take a look at what this can do. So here's another rigid chiral molecule, 3-carine. I'm showing you here some solution phase measurements, and vapor phase measurements are 2 favorite points. So there's a big difference. What if we now do calculations on the isolated molecule behavior? If we go ahead and do either density functional or coupled cluster for isolated molecule behavior, we see we get very similar behavior. Both seem to be doing pretty well. Now what about how do we think about solvation? So historically, solvation has been treated by putting in a correction for local field effects. This Lorentz local field correction is basically the ratio between the microscopic electric field acting on the solute and the macroscopic electric field that exists in the incident or applied electromagnetic wave. And historically, this was basically obtained by modeling the dielectric polarization of the surroundings as a random ensemble of point molecular dipoles subject to an isotropic electrostatic field. So it would say that in a solvent, the optical rotation should be related to the optical rotation in the gas by this correction factor. The correction factor involves index of refraction squared plus 2 divided by 3. For any real solvent, the index of refraction is greater than 1. So it should say that, in a solution, you have something bigger than 1 multiplying what you measure in a gas. 5 minutes? Oh, okay. So it's telling us that what we should see is that the optical rotation should be larger in a solution than it is in the gas. Clearly, that's not the case. This is not a good description of local field effects. Okay, what about if we think about the polarizable continuum model, okay, where we carve out a shell in the continuum dielectric solvent that mimics the shape of the molecule, and we treat the solvent as a continuum dielectric. If we go ahead and do that, It would predict for the limiting cases of acetonitrile and cyclohexane, the limits of low polarity and high polarity, that again we should have a solution phase optical rotation curve that is of higher magnitude than the vapor phase. So clearly, that's not working either here. What I can tell you is, again, the behavior is not intuitive, because it seems we're able to get the best mimics for what we see in the vapor phase by solvents of high polarity. And I want to just point out, polarity is the concept that chemists like to think about, but polarity is a static concept. The concept that one should be thinking about is polarizability, the frequency-dependent analog of polarity. Acetonitrile has a high polarity. It has a high static charge distribution. On the other hand, it has a low polarizability, like a vacuum which has no polarizability, because it holds on to its electrons very tightly. Water also has a low polarizability, so it sort of mimics what we see in the vapor phase. In the time remaining, where I'm going to talk very quickly, I want to tell you about some more recent work, and these are experiments done in collaboration with Daniel Crawford at Virginia Tech and Marco Caricato, now at the University of Kansas. And this is looking at an anomalous molecule, a molecule norbornenone, where we have an enormously large optical rotation, and trying to understand why we have an enormously large optical rotations. So at sodium D-line rotation, at sodium D-line excitation, the optical rotation is about 1,000 degrees. Typical molecules of this size have rotations on the order of tens of degrees. So this molecule has something like 50 to 100 times larger optical rotation. You can see that there's a very small solvent effect. This is, cyclohexane and acetonitrile, the two limits of polarity. And so when the first calculations were done on this molecule, calculations done in the vapor phase, there was a density functional calculation in red, a couple cluster calculation in orange. Clearly, density functional theory agreed better with the available solution phase data, and this was thought to be evidence that density functional theory is clearly giving you the right answer, and couple cluster theory is wrong. On the other hand, if we then went ahead and did the measurements in the vapor phase, and you can see the measurements in the vapor phase are far removed from the solution phase results. There's a giant phase dependence here. And in fact, this is a case where that Lorentz local field correction actually seems to work. But there's a big difference between the vapor phase and the solution phase, so much so that now on a percentage-wise, coupled cluster is doing better than density functional theory. So why does this molecule have a gigantic optical activity? This is the predicted optical activity at sodium D by density functional theory. Could it be because it has two stereogenic centers and therefore it has twice as much optical activity? No, the carrying system that I showed you before, as well as the pinene system that I showed you before that, also they have two stereogenic centers. They don't have giant optical activity. So what could be the reason? And to paraphrase Albert Einstein, if you're thinking about a complicated problem, try to make it as simple as possible, but no simpler than that. So let's take this molecule and pull off almost everything. So pull off a lot of the carbon atoms, and we're left with this little fragment. Now, this little fragment could never exist in that structural form because it's not rigid. But that little fragment no longer has a stereogenic center, or two stereogenic centers. It now has a stereogenic plane. It has a chiral plane. And if now you compute the optical activity of that fragment, it's twice as big as the computed optical activity for norbornenone itself. So clearly that fragment has in it the essence of what's going on. Let's take that fragment and now see what happens when we rotate about this carbon-carbon bond. We're doing that because here we have a light-absorbing chromophore, a double bond. Here we have a light-absorbing chromophore, a carbonyl. The bottom plot is going to show what happens to energy as we rotate about that bond. The top plot is going to show what happens to optical activity as we rotate about that bond. Okay, so the energy you can see changes for this fragment. but the optical activity is having profound changes, right? It's going from essentially 0 to numbers that are gigantic, okay? Now, in actual norborneinone, you have the two chromophores being held rigidly in space by a carbon skeleton of minimal complexity. And that, for norborneinone, these two fragments are being held in this configuration, which is almost optimal for maximizing the optical activity. So what we have occurring in this molecule are coupled chromophore dynamics. We have this double bond functionality, an alkene functionality, and this carbon-oxygen functionality, a carbonyl. Both of them have transition moment character, and they're being held at the right orientation and in the right configuration to maximize the coupling you need for optical activity. In fact, the optical activity in this system is dominated by the lowest electronic transition. If you remember the theory I showed you before, you had to sum over all the excited states of the molecule. This is the only case we found where that is not true. The response is totally dominated by the first excited state, which turns out to be an N-to-pi transition which on the carbonyl, which has a strong magnetic dipole moment. But in addition to having that N-to-pi star transition, you have charge delocalization. You have delocalization of character between the carbonyl and the alkene behind, and this induces the required electric dipole moment transition. And to make this happen, you have to have a coplanar arrangement of the alkene and the carbonyl functionality. But the magnitude of the response, don't forget, is a dot product between the magnetic and the electric dipole moments. So they have to have the right orientation. In norborneinone, they're held in the right orientation, opposing like this, so that you get a maximization of the transition dipole moment. So all of this in norborneinone would seem to depend on this low-lying N-to-pi star transition. So in our latest experiments, we've tested that. We've taken that N-to-pi star transition in norborneinone and gotten rid of it through the magic of chemistry. Right? Replace the carbonyl with now an alkene, so you have methylene norbornene, and now you no longer have that low-lying transition. Now you have to sum over all the excited states of the molecule, and we would expect that the optical rotation should be substantially smaller. If we go ahead and do experiments, and these are some of our latest experiments, yes, it is smaller. It's smaller by a factor of 4 and maybe a factor of 2 over here, but it's still pretty big. And that's because both of these molecules have what we call inherently dissymmetric chromophores. We have two light-absorbing chromophores that are separated by a substantial distance and are being held in the right orientation to generate electric and magnetic transition moments that are maximized to couple to one another. And I'm going to finish now. So summary and conclusion. I tried to tell you about cavity ring down polarimetry. It's a very sensitive technique for interrogating both dispersive and absorptive optical activity. We're still working on the absorptive part, I might add. I've shown you that solvation can influence chiral optical response profoundly, so much so that it can change even the sign of the behavior. Rigid species, counterintuitive solvents of high polarity are the ones that mimic what we see in the vapor phase. I didn't talk so much about conformational flexibility, but I did show in that methyl rotor for methyloxyrane, simple methyl group rotation can make the optical rotation go crazy. Molecules that are not structurally rigid that have different conformations, same sorts of things can happen. Continuum dielectric scaling doesn't seem to work, right? If you just take a progression of different solvents of different dielectric constants, there isn't a uniform scaling from, high dielectric constant solvent to low dielectric constant to the vacuum. And we really believe that the scaling with frequency-dependent polarizability is what people should be thinking about rather than scaling with static polarity. I'd like to finally thank the folks who funded this work to make it all possible. to thank members of my research group who have been involved, certainly, oh, I keep using the laser pointer, who have been involved in this particular aspect of the research, and other members of my group are involved in completely different things. And this is our honorary member of the group, Joshua Willard Gibbs, who happens to be entombed very close to the chemistry department at Yale. And finally, in a bit of advertisement, if you're interested in chirality, I encourage you all to go to the upcoming national meeting of the American Chemical Society, where Marco Caricato, who many of you might know is a student from this institution, and I are co-organizing a symposium covering all aspects of molecular chirality. And I thank you very much for your attention, and I'd be more than happy to answer any questions you might have.
Thank you very much. And now we have time for questions, comments.
Answers? Don't make it hard.
I have first a very naive question, and then a more technical one.
Oh, okay.
About the ring down cavity. How do you actually count the number of reflections?
Yes, you don't have to count, because let's realize that we're injecting a pulse that, let's say, is 10 nanoseconds long. The pulse is therefore, 10 feet long, if you want. Okay, I'm imperial units, sorry. And the cavity itself is maybe 3 to 4 feet long. So it's not like this pulse is actually bouncing back and forth. The pulse is occupying the whole cavity. So what we are actually measuring is time. We're measuring, we know when the light is injected very precisely, and we're measuring the length of time since then using an exponential decay profile. So don't have to measure the number of trips, because we actually know how long the path length is from time, because light is traveling at a given speed.
Then the more technical issue is when you substitute the ketone with a second alkene.
Yep.
You're actually losing a low energy transition, but you're making almost degenerate.
Yep, excited, yes. But again, the transitions that we're making degenerate are much higher up in energy. Yeah. Yes.
So you expect possibly a larger extone coupling, but
far removed.
Far away.
Yeah.
Okay.
I will say that we also, if you do a calculation, okay, in the limit of infinite wavelength, so you can't really do that, but essentially not dismissing any resonant enhancement. It still shows that there is a decrease in the optical rotation for the methylene norbornene by maybe a factor of less than 2 or so. Okay, and that's sort of, it's a calculation, so we can believe or not, but that's sort of removing resonant enhancement effects. So there is a decrease, but the decrease, I think, is because you are losing a direct magnetic dipole from a chromophore. And everyone has said that direct magnetic dipole is important, but I'm trying to say it really isn't as important as you think. And perhaps from what you're saying, because you have coupling of these near helical arrangements of the two alkene functionalities.
Yes, very nice. I wonder, since you've shown this example of norbornone, and where you say there is this gigantic activity, if you can also from there get some information or some ideas on how to find something which is as even higher.
Yes, definitely.
There's some structural pattern.
Yeah. So
if you can get it.
So that norbornone has encoded in it the ingredients you need. The ingredients are you need to have coupling, right? So you have to arrange to have coupling. You also have to have orientation. Orientation has to be right to have coupling, but orientation has to be right also to have the magnetic and the electric dipoles lined up. Sure. So norbornone naturally, the way it comes to us, right, is almost perfect, but not quite there. So you certainly can get ideas of how you might synthesize a molecule that is even going to have bigger optical activity.
Would be nice to find.
But that's linear. You're interested in nonlinear, and I can't tell you that at all.
The second question, if I may, in fact, was about nonlinear,
Yep.
because I like nonlinear much more than linear, as you know very well. And then I wonder, I've seen something long time ago about nonlinear optical rotation like this. And I wonder if there's still work going on around these things, and in particular if experiment has processed anything like that.
I think now there has definitely been, and everyone will agree, an experimentally verified nonlinear CD. Okay, but nonlinear optical rotation, I'm not sure.
I think that there was a paper a long time ago about that.
Yep.
I think it's amenable to theory, and I think we never did the real calculation about that because there is no experiment around.
Yep. I mean, to make, I know a little about that, I guess I even forgot, because when we first published our work, one of the things that a referee told us is they were sure we were doing nonlinear optical rotation. I will point out our cavity, we have these reflective mirrors, so 99.995% of the light that we inject gets rejected. The amount of light in the cavity is about 5 orders of magnitude lower than what those previous papers, and these are probably the same papers you're thinking about. Yeah, so there's no way we're doing that here. In theory, with the right cavity techniques, we could even enhance the field and might be able to do it, but we haven't tried to do that.
Does it work? Okay, so I was very pleased to hear that Cobble Cluster got it right for Bissell Oxrain. But can you just explain what model was? Was it CCSD?
So that model was CCSD, but it was using a split basis. I believe it was a double zeta basis on carbons. I think it was a triple zeta basis on the oxygen, and it might be a double augmented double zeta basis on the hydrogens. But you'd have to check the original paper for that.
Pretty good.
Yeah.
I have a question about the experimental setup. Maybe I missed. Which is exactly the component or a set of components which limit the bandwidth?
May I go back to, yes. If I can. So to make this work, you have to have as long a lifetime in the cavity as possible, because lifetime is proportional to the path length that you're going through. So that means these mirrors have to have very, very high reflectivity. The higher the reflectivity, the longer the lifetime of light in the cavity, the longer the path length that you're passing through. Also, because we're putting optics inside the cavity, these optics have to have the best anti-reflection coatings you can get. It turns out it's easier to get reflective coatings than anti-reflection coatings. So the anti-reflection coatings we have here are on the order of 0.1% per surface, reflective loss. And with that, if you don't have those optics in the cavity lifetime is probably tens of microseconds. Those optics, put them in the cavity, it reduces the lifetime to microseconds, so probably by almost a factor of 10. And that's what limits in terms of being able to move wavelengths substantially. There are other technical things that limit us, but the idea is those reflective and anti-reflective coatings can only work with high efficiency over narrow ranges of wavelengths. It is actually optimized for that particular wavelength. Broadband coatings are broadband, but they're not very good. Right.
A curiosity, because you were showing cases in which the average on the vibrational states was important, then you were showing cases in which the coupling between electronic states is important. Mm-hmm. So I don't know how exotic it is, but are there cases in which, let's say, the non-adiabatic couplings are important? Coupling mediated by vibrations.
Yes.
Because if I can add, there are cases, for example, in electronic circular dichroism, where this kind of coupling, even in the Hertzberg-Teller formalism, give rise to alternation of signs. If To go close to resonances with optical rotation, in those cases, what do you
We haven't done it, but yes, I believe you would, because don't forget the CD profile and the optical rotational profile are Fourier transforms of each other, really. And so I do believe if you could make this, and we would like to do this, there are technical reasons, make it into a scanning kind of an instrument, we would see those sorts of things, right? And I do believe there are vibronic interactions that are most important when you are close to resonance. That's where they'll manifest themselves most. Certainly they must be involved here also, but so many other things are involved that they're really being washed out in many ways.
Are there any other questions?
A simple question from a non-technical. I mean, you told us like that there are different contributions for the optical rotation, and I was wondering if putting like a static field, like magnetic field, could like enhance one mode or the other, and it could make maybe, I don't know, show differences in the measurement.
So two answers. There are different kind of phenomena called magneto-optic chirality or magnetically induced chirality. It turns out with a magnetic field, you can even take an achiral molecule and it can behave in certain aspects like it's chiral and give you signatures. And actually in our apparatus, it would give you no signature because we have those intracavity elements. If we were to take those intracavity elements out, put in an achiral molecule and put on a magnetic field, we would get a signature. So there are phenomena like that one could see. They're not natural optical activity, on the other hand. On the other hand, if there was some way to take a chiral molecule and orient it in space and do a measurement, maybe using an electric or magnetic field, that would be very good because what we right now measure is in many ways the trace of a tensor. By being able to align a molecule, we can maybe measure tensor components. The downside of that is once you take molecules and align them in space, you create a giant linear birefringence, which is much bigger than the very small circular birefringence we're trying to detect. So it will provide an enormous background. But measuring things with magnetic or electric fields to align is a very, very good idea. And I think there are ways to do that. Not with this experiment, but with nonlinear optics. So that's something we're trying to do.
Okay, so I have many, but I will
Okay.
ask you later.
But you have to give me the answers, not ask questions.
Oh. And so, thanks again, and thank you all for coming. Now we have the class.
I talked too long.
That was perfect. Also for